So, if crypto stuff you want to know, just listen to this guy called Joe. He knows Rust TLS for securing access. So let's look at what he's going to show.
Thanks. Can everyone hear me? Excellent. Right, so this talk is in three parts. So I'm not assuming that you know what TLS is or does. So that's the first part, is like, what's this all for? The second part is, I want to write a thing in Rust. What crates are available to me to do TLS? And then the third part is like my thing, which is called rustls or Rust TLS, if you like. It's a bad name. I regret it. So yeah. So TLS, first of all, is transport layer security. It's not thread local storage. If you're here for a thread local storage talk, I'm sorry. But it's also known as SSL, and in common usage, SSL is actually more common. It's like the S in HTTPS. It's your padlock in your browser, which is very, very common. It's like HTTPS now is more common than HTTP, which is awesome. Very good indeed. Very happy with that. So we're going to talk about goals. What's the point of this thing in really high level terms, not very low level technical detail. A bit about the history, and then a bit about kind of the security history, because it has a long and kind of checkered history when it comes to actually achieving those goals. So we've got our cast of characters here. These are normal, like commonly used characters. We've got Alice on the left, who wants to talk to Bob, the clown, on the right. And then we've got Eve in the middle, who's, in this case, Eve is an eavesdropper who's just watching traffic going back and forth. Alice and Bob are really concerned that they don't want Eve to be able to learn much about their traffic, their communications. So that's one thing that TLS aims to do. The next is like authenticity. Alice wants to know that she's actually talking to Bob, and not Mallory in the center, who suspiciously looks like a lot like Eve. In that case, maybe she's the same person. TLS also, as a kind of secondary but not commonly used option, allows Bob to authenticate Alice as well. Not very commonly used, quite used in enterprise settings, but not on the web. And the last one, which is kind of related to authenticity, is like integrity. So not just integrity in terms of bits and bytes going over the wire, but integrity of the whole communication. So that includes things like replay. So if I send a message saying, deposit €1,000 into this account, someone shouldn't be able to take that message and send it to the server a second time and have the server accept it. That would be obviously a bad thing. So yeah. There's also a kind of related thing which doesn't really work in practice, which is like truncation resistance, which is kind of like similar to the replay problem, but at the end of the communication. And the reason that doesn't work is because in general people aren't willing to treat TCP closures of the TLS channel as a security problem. It's just like, the connection went away. I don't know whether that's because it's the internet or because there's someone trying to attack me. So watch out for that if you're ever designing a protocol. Like, you imagine a database a transactional database thing where your first message is start a transaction, your last message is commit the transaction. So if an attacker can chop off the commit, that can be quite disastrous. So this is a bit of history. SSL1, ignore SSL1, it didn't exist basically. The first time it was ever presented to anyone, someone in the audience broke it SSL2 also quite bad. SSL3 was the first one which was actually designed by like a cryptographer, and that worked really well. But they only gave the chap 2 weeks to do it. So yeah, and then it kind of changed name, but you shouldn't think that SSL3 and TLS1 are really that different. They're really, really close protocol-wise. And that was because it transferred from Netscape to IETF. But yeah, you can really think of SSL3 to TLS 1.2 as being really the same family of protocol. TLS 1.3 is dramatically, well, not dramatically, but very, very, very different. Way, way more different than 1.1 to 1.2. There was quite a disagreement in the TLS working group about whether TLS 1.3 was the right name for it, whether it should be TLS 2.0. 1.3 kind of won out because it had already been used and talked about, and there was lots of security papers, like security results saying, yes, we proved this is secure, talking about TLS 1.3, and they wanted to avoid that confusion. This is how it's deployed. So the important thing to note is like, well, these percentages don't add up, and the reason they don't add up is because a given server can support more than one at a time. So really, you should interpret this as like, if I go to any of these servers in this data set, the probability of them supporting TLS 1.2 for a given random server there is like 90-odd%, and the direction is nice. The one we think is good is going up. All the ones before are kind of going down, some quite slowly. And this is like the security status, like how much you could distill the security status of these complicated protocols into one slide, right? So 1.0 and 1.1 are quite very close. 1.2 has some good options, but also inherits most of the stuff from before. So you have to kind of pay attention to your parameter choices. And TLS 1.3 is very new. It's not even standardized. It will be in like a matter of weeks. But it throws away all the old stuff, which is nice. So I want to spend a little bit of time on this slide talking about these countermeasures. So these are all implementation strategies for dealing with kind of design faults, really, that came in around 1996 and haven't been removed, as I said, until like today. And people will go, well, why don't you just implement the countermeasures? It will be fine. There's some problems with that. One is that the aims of the countermeasures and how to do them isn't documented anywhere. For example, the IETF doesn't publish or hasn't published any implementation guidance saying this is what we're trying to do and this is how you might do it. And as a result, they're quite under-tested and difficult to, they're just unconvincing. They're also sometimes quite uncommon. For example, Golang's TLS library, which is really, really good, started off its life without any of these countermeasures, and even now has fewer countermeasures in the same, like countermeasures for the same bug than OpenSSL does. So you're kind of reduced to thinking, like, just worrying about this, like, do I need all these things? Do I not? The other thing, which is slightly more serious, is in 2013, OpenSSL implemented one of these countermeasures, and it had a bug in it. And that bug stayed there until 2016, and the bug was worse than the bug that they were writing the countermeasure for. So this wasn't a triumph, really. So let's not. I mean, we don't have to, so let's not. I mean, if we did have to, then that would be a shame, but okay. So there's also this like modern TLS terminology. I use it in the title of this talk. And I'm not just making stuff up. It's like quite commonly talked about. I think Mozilla really brought it in. This is from their wiki page about configuring servers to have good TLS. Cloudflare has it as an option. Apple has a similar thing but called it a different name. As they do. Yeah. So let's talk about Rust a bit. This is like the diagrams I'm going to use. Orange box is a crate. Grey box is not a crate, is like another library. White arrow is a useful Rust API. And yeah, so we've got OpenSSL and S-channel and security framework and NSS bindings. I'm missing out all the -sys crates here because they're kind of, just consider them, they're part of that line, right? And then we've got some implementations. There's my one. There's another one, which is BTLS, which is not very widely known about, but is very interesting. It's like an all-in-one thing, like more to the scope of OpenSSL, and it's very interesting. So go and have a look at that. It's not on crates.io, but it is written mostly in Rust. And then we've got some abstractions. So native TLS is really, really common, very widely used, probably the most widely used way of doing TLS in Rust right now. Yeah, so it's basically, we have these bindings. Let's choose one based on what's the most convenient for the platform I'm running on, and that really works very well. And it's it's very low friction. So if that's what you want, this is a good choice. There's also this one, which I really do like. So there's TLS API, which is just like a collection of traits, and then these intermediate ones, TLS API, OpenSSL, etc., which provide implementations of those crates. So if you're writing a library and you're not quite sure what TLS library your kind of application level consumer wants to use, you can just make your library generic on those traits, and then your application at the top just passes in one of these choices. And that works really well. It did come after native TLS though, and if you kind of, in your mind, pick out native TLS, it's kind of doing the same job twice. One is providing a generic abstraction over TLS, and then native TLS is doing the same thing but at a different level. So that would be good to fix, although I'm not sure it's really worth fixing at this point because there's a lot of native TLS users. But yeah. And then Tokyo, right? So it's a whole nother level of, oh my God, what's happening? And yeah, there's another similar set of things which glue Tokyo to TLS, like gluing it straight to OpenSSL, gluing it to native TLS, gluing it to the whole like subgraph of TLS API implementations, and that's really interesting. And then gluing it to rustls as well if you want. So speaking of which, so I made a logo on Monday, and I made stickers. I'm not a graphic designer, you can probably tell. But yeah, so this project is an implementation of TLS 1.2 and 1.3. And when I say 1.2, just the good bits, right? And in general, in TLS, just the good bits, it's not comprehensive like OpenSSL is. So I've got quite a background in kind of security-oriented software development, and I've written a couple of TLS libraries, proprietary ones, in the past. So I've been studying this kind of area for, well, really most of my career. So yeah, this is like the whole the aims of the project. This kind of came after I started writing it, so it's a bit post hoc. But really the point is, only good stuff. Try and talk to about 95% of other things. As you can see from the earlier things, almost there, not quite, and I'm kind of like aiming where things are going rather than where they are. No unsafe Rust, so there's no unsafe blocks in this crate. It does depend on others, which obviously have unsafe behavior. Well, not unsafe behavior, but unsafe blocks, let's say. And trying to present a really simple API, which kind of just looks like a pipe, right? So you put your bytes in here, maybe it's a HTTP request, you get TLS out, and likewise from the other end, you put TLS in and you get your HTTP response back. So yeah. And it's almost 2 years old now. Like tomorrow it will be like properly 2 years old, because the first commit doesn't really count because it's just a big load of non-working code. Yeah, I'm very pleased that there's a few contributors. So that's good, I'm very happy with that. And testing, right, so testing, very important. I'm not gonna, afterwards in the coffee break, I will happily tell you a anecdote about my interaction with reporting a moderate level security vulnerability to OpenSSL and the testing that happened around that, but not here. So we've got quite a lot of tests and 97% line coverage, and that's of like 6,800 lines of code. In comparison, OpenSSL's automated testing is about 65%. But that is like the equivalent of 40,000 lines of uncovered code that they ship in every release. Oh, scary. So let's talk a little bit about performance. I'm going to there's blog posts which are kind of expand on this section. So if you really want to look at the details or reproduce the results, then go there. But just to say that a TLS connection kind of starts with a handshake, which involves lots of public key crypto, which is quite expensive. And then it goes into a data transfer stage where there's no public key crypto, but really what you're trying to do is take your data and shovel it at the fastest crypto implementation you can find without, copying it too much or really just getting in the way in any other sense. But there's also a way of shortcutting the public key crypto if you've talked to a server before, and that's called a resumed or abbreviated handshake. So that's also interesting for performance because in practice, so if you're doing HTTP, typically what you'll do is you'll go and do a full handshake with the server, and then maybe you'll open a few more connections to the same server to do other sub-requests. Those other connections will tend to be resumed. And then we just go into the same data transfer stage, right? So rustls does quite well here compared to OpenSSL. And at the bottom there, you've got the link to the blog post, which should have stuff that you can reproduce this with on your own hardware. But yeah, the headline is that both libraries can comfortably do 25 gigabit Ethernet, which is not hardware that I have. I just don't have that kind of money. The difference here is basically that OpenSSL has an extra mem copy in the sending direction. Rustls doesn't, because when we get data from the application, we just borrow it to encrypt it rather than copying it and then encrypting it. So that's like the beauty of Rust, I guess. And then this is resumed handshaking performance. So this is quite a lot better, but I haven't fully understood why yet. I think OpenSSL is doing quite a lot more per connection. Well, obviously it is. But yeah, I haven't really looked into what precisely it's doing. So take that with a little bit pinch of salt. And the full handshake performance is a little bit worse, well, quite a lot worse for rustls, but there are coming improvements in Ring. So it should make it roughly the same, like 1.7, 1.6 slower. And then once we're there, we're going to have a look, I think, at making that equal. And you may think, oh, 1600, that's actually really, really slow. But this test is specifically quite artificial, so it has an artificially long certificate chain, just to really exercise as much different paths of public key crypto as possible. So now I want to talk about a fairly famous, well, infamous security failure in Apple's homegrown TLS library called Secure Transport, and you might have noticed earlier there were some bindings to this. It is today quite well regarded, so don't let this worry you. But the interesting thing about this is it's kind of open source, but they don't develop it in the open, so they just drop source for every release. And someone noticed, or maybe through testing, I don't know, that between two releases, this line just appeared. There were other changes in the file between this release and that one, so I think the current thinking is it's like a merge hazard that's happened where someone screwed up a merge and duplicated this line. Unfortunately, that goto is executed unconditionally, right? Because this isn't Python. And so it skips over this SSL raw verify, and you may think, oh, SSL raw verify, is that important? Yes, it is. That's the authenticity thing that we were talking about earlier. So for quite a while, that whole library had no authenticity checks whatsoever, really, which is a shame. So I thought about, let's take that as a problem. Like, the problem is I use Vim and it's chaos, and maybe I'll make an error like this one day. Well, first of all, I'd like it not to compile, really. But failing that, can I make it? What can I do? What can we do, right? I came up with the conclusion that really the problem in this code, is ignore the fact that obviously there's a lack of testing here. The problem in this code is that there's nothing positive coming out of this function. It's just like the return value from this function is 0 if there's no error, or an error code. In practice, all error codes are treated the same. They're like you're being attacked. So returning 0 is not actually very helpful when there's all these possibilities of returning 0. So let's actually encode this in the type system and have a type which explicitly says, I have verified this signature, and only create that once exactly in the bit of code which verifies the signature. And once we've got that type, let's take it from up here where the verification happens and weave that type into the whole rest of the session, so that you can't get down here in the important bit of the session without having been up here and made this type, having done this verification. And that's cool. The type system's awesome. So this is what it looks like. So this is a particular verification. It's not exactly the same one that Apple were doing, but I'm trying to be brief with this code snippet. So we want to verify that this thing that we got is the same as this thing that we computed. And only then we make one of these values, and then this struct down here is like the terminal state of the TLS session, where you're encrypting data back and forth. And we have all these different 0 size types, which have only been created further up earlier in the connection. And that basically means that if you screw up this bit of code, then the compiler won't let you get to here. And all you have to do then is it's a code review task of looking for this finish message verified assertion function and convincing yourself that the only path to get there does actually do the verification. How am I doing for time? Oh yeah, cool. I used to have like this big list of stuff to do in the future, and it keeps being ruined. One of the things was write some glue for use in non-Rust programs. So my idea was actually Python, but and then someone went and did it, so that was cool. So this is very interesting. It's called MesaLink, and it's basically a C library shaped box with an OpenSSL external interface containing rustls and ring and all the other stuff that rustls depends on. And the idea with this is that it's part of a new Linux distribution called Mesalock Linux. And they're just like taking large chunks of unsafe code, in this case OpenSSL, and swapping them out incrementally. That's a really interesting, incremental approach to, you could either rewrite the world, or you could start rewriting the world in little bits. And I think that's really cool. So I'm very happy with that. I had no idea that was happening, and it's just like, oh, a thing, amazing. The other thing I want to work on in the future is verification. So testing is good. Testing with high coverage is good, but it doesn't actually prove much. It really, if you get good coverage, it proves that your tests aren't bad, but it doesn't prove that your tests are good. If you're not covering the lines, then you definitely don't have good tests. But verification is a whole lot stronger. It's like we have this abstract description of what the protocol should be. Does that match the concrete description in the code of what we're doing? If they do, then that's excellent. And if they don't, if they differ, that's probably a bug, and it means that rustls is implementing a protocol which isn't, strictly speaking, TLS. This has been done, so I'm planning to reuse some of the work from S2N, which is Amazon's in-house proprietary, well, not proprietary, it's open source, TLS library. But yeah, they've done this verification on their implementation, and it's quite simple, but it's a start. It's like, once that is going, then it should be possible to write automated verifications for things like replace the code review step in the previous slide. Just make sure that this function produces this type, and then let the compiler deal with all the rest of it. And that is it. That's the repo. That's my slides if you want them. And there's a test server if you want to hit that. Yeah. Do I have time for questions?
Yes, you have 5 minutes.
Oh, cool. Any questions? Yeah. Do we have microphones, or should I just...
You have 2? Please raise your hand.
Thank you. Great talk, by the way. In one of your previous slides, you said you're using a safe subset of Rust. Could you explain a little bit more what that means?
Yeah, I just mean no unsafe blocks.
Okay, thank you.
Yeah, sorry.
Okay, so about the possibility to introduce subtle bugs, I've heard, but I'm not really an expert, but I heard that sometimes there are timing bugs.
Yeah.
And I was wondering if there could be something that could be done. So are you doing something to prevent them systematically or not? That's the main question.
So that's an excellent question. One of the scope of rustls is kind of like the protocol, and that does have some steps which need to be done in constant time. But really the most important bits which need to be done in constant time are done in the crypto library in Ring. I definitely trust Brian Smith to get that right. And to some extent well, I shouldn't say to some extent, to a great extent, the boring SSL people as well, which is like the ultimate source of quite a lot of the code in Ring. So yeah, I'm not saying not my problem, because it definitely is, but not to the extent which it is in OpenSSL, where it's like a bigger scope of project, which includes all the crypto, all the TLS protocol, and yeah.
Hi, Dan here. You mentioned earlier that you have a story about reporting a bug to OpenSSL. Do you have time to tell the story now, or?
Not in front of a big load of people now.
Oh, okay, fair enough.
Hi, I was wondering how much effort was it to achieve the 97% test coverage?
Yeah, actually not a huge amount. It was a lot of effort to get from like 94 to 97, but getting to 94 was very easy. I just want to like shout out to the BOGO, the Boring SSL Test Suite. That's like a really, 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 it's like the Golang TLS library, but really evil. So it like connects to you and then sends the wrong message, and then connects to you and then sends a different wrong message in a very targeted way. So that was really, really awesome in order to actually test the library. Without that, I probably would have had to write something equivalent myself, and that's just no fun at all. So that gives me like a lot more happiness about the state of it, because it's being tested like kind of independently.
So we all really like, I think, Rust for the safety part. But since most of us don't write all the application in Rust, what a lot of people do is they write these libraries that you can consume from C and then Python and so forth. And it happened more than once to us already that the actual unsafety was in the C binding or then the consumer on the Python side. And so you mentioned before that there was Mesalink, which tries to expose rustls as OpenSSL compatible API. Do you know if there's do they do some auto generation there to verify that these bindings are safe, or do you know if there's a project that does this?
I'm not aware of a project which does that, and I'm not really totally sure how Mesalink works under the hood. Obviously, with the OpenSSL API, it is an interesting API. It's probably not, if you were looking for like a safety-oriented C API for TLS, it's probably not what you'd write. There are better C APIs, like the one that LibreSSL came up with called libTLS. That's probably what most people would come up with if they were writing a TLS API for C. But no, yeah, I'm not aware of any projects like that.